Hello, in this lecture, we are going to discuss a slightly modified, you can say, the Dirac Delta potential that we were discussing in the previous lectures. So right now we are doing one-dimensional potential problems in which we are discussing Dirac Delta function. Dirac Delta potential. So we've already discussed an attractive Dirac Delta potential centered at origin. Now what if I slightly modify a particle, slightly modified my potential? So for example, let us consider the case where your particle of mass m is subjected to a potential of the form if I say this. So for all x greater than 0, you have you have only one negative sort of, you can say, Dirac delta potential, and that is around x equal, that is centered around x equal to a. So at x equal to a, you have an attractive Dirac delta potential, and for all x less than 0, you have an infinite potential. So probability, so you have this, your wave function here would be 0. That is certain. Your wave function here would be 0 since potential here is infinite. I hope it is clear. Now, we want to find the existence of bound states. We want to find the existence of bound state, and in fact, we will and at the end, as we go ahead and solve this particular problem, we'll find that these bound states, there would be a dependence upon the value of a. There would dependence upon value of a. That is, only if there is certain value of a only, there will be a possibility of a bound state. So let us see how to approach this particular problem. So, okay, as we know, the Schrodinger equation would be given by d square upon d psi square plus 2m v upon h ket square minus 2m e upon h ket square. This is, I think, sorry, this is equal to 0 because minus h ket square upon twice m. So I've just multiplied it by minus 2m upon h ket square. This is it. Now I already know that my potential now is given by minus v naught Dirac of x minus a, and accepting a, for all points this would be 0. So what I would do the same strategy that I did in the previous lecture. I will find the solution for all x not equal to a. Okay, because at x equal to a, it is difficult to find a solution. So I'll find the solution for x not equal to a. And since I know that for physically realizable solutions to the Schrodinger equation, my psi x must be a continuous function. It must be a continuous function. Okay, this is clear. So let us try to do this particular problem. So in this particular problem, I will first write the entire thing so that doesn't bother you much. And then you know that since we are talking of bound state, so energy must be negative. So I can write my E as minus of modulus of E. So this will be, I think, plus E minus 2m modulus of E upon h ket square is equal to 0. Overall, for all x not equal to 0, for all x not equal to a, your Dirac delta function is equals to 0. So accepting x equal to a, so this is it. So I will write here it is 0, here it is a. Now for x greater than a, x less than a, or you can say that you're exactly at x equal to a, your Dirac delta function will be infinite, but except that it will be 0, so this will become 0. So I will write d square psi upon dx square minus k square psi is equal to 0. And the solution of this particular differential equation comes in some linear combination of e to the power minus kx and e to the power kx. Okay, so for all x greater than a, I cannot have this term. I cannot have this term simply. And for all x less than a, here my wave function is 0. Remember, here my wave function is 0. That is, for all x less than 0, my wave function is 0 because there is an infinite potential here. For all x belonging to 0 in a, and for all x greater than a, there would be the wave function written in some forms of e to the power minus kx or some linear combination of e to the power minus kx and e to the power kx. Let's see how to go about it. So for all x greater than a, I cannot have this term. So here I can only write it as e to the power minus kx. So I can only have this term. Here both the terms are allowed, no issues. E to the power minus kx can be there and e to the power kx can also be there. So in short, I will try to write the wave function in this fashion. So I'll write a e to the power kx plus b e to the power minus kx for all x lying between 0 and a. I will write c e to the power, I think, minus kx for all x greater than a. X greater than a. So for all x greater than a, I will write c e to the power minus kx, and for all x lying between 0 and a, I will write a e to the power kx plus b e to the power minus kx. Now, according to the continuity condition, that is, according to the continuity of wave function must be continuous at x equal to 0 also and x equal to a also. So at x equal to 0, to the left of it, your wave function is 0. So 0 should be equals to a plus b, and which says that b should be equals to minus a. So this is the first thing that we can obtain from continuity condition at x equal to 0, and at x equal to a, it will be a e to the power ka plus b e to the power minus ka, and since b is written as minus a, so I'll write minus a here, should be equal to c e to the power minus k. Okay, so overall this is it. Now you can see there will be two conditions. One condition is that b should be equal to minus a, and second condition yields me that a e to the power ka minus b e to the power minus ka. Sorry, this will be minus b is written as minus a should be equals to c e to the power minus ka. So this is your second. So your first you know, second you know. Now, as we wrote in the previous, as we saw in the previous lecture also, in order to counter all these kind of differential equations which involve Dirac delta function, we integrate the differential equation in the region where your Dirac delta function is there. So, for example, here your Dirac delta function is stationed at x equal to a. So we'll integrate from a minus epsilon to a plus epsilon in order to extract back some meaningful results. So, for example, here we want to find the bound state, so it will yield me some energy kind of thing. So you have a e to the power ka minus a e to the power minus k is equal to c e to the power minus k. This is second equation that we have written from the continuity condition at x equal to a. Now we are integrating from a minus epsilon to a plus epsilon. We'll get d psi upon dx from a minus epsilon to a plus epsilon. I think there is a term which I will have to see, plus 2m v naught upon x ket square. You had some psi of x, or if I'm not written psi, please do write a psi here. My mistake. So here it will be a psi also. My mistake. Now, okay, psi, and then you have a Dirac delta function here, and then you have this is equals to e psi dx integral from a minus epsilon to a plus epsilon, and similarly here also you have an integral from a minus epsilon to a plus epsilon. Now, as we did in the previous lecture, this integral would go to 0. There would be some 2m's, and I think that also would be there. Concentrating right on there, right now over there. This entire integral would become 0. Why this entire integral would become 0? So this is constant, this is constant, this is constant, this is constant. This will come out. An integral psi from a minus epsilon to a plus epsilon would yield me some psi a plus epsilon minus psi a minus epsilon. Epsilon tends to 0, so this will get cancelled. So overall, this will get cancelled. But one that is situated at x equal to a, this integral, because this is because here is a Dirac delta function, this integral has this kind of Dirac delta function here. So you know that this Dirac delta function at x equal to a is there. So if I integrate, it will filter out me the value of the wave function at the point a. So what is good is what you will get here. This will be some non-zero integral, and this will be d psi upon dx at a plus epsilon minus d psi upon dx at a minus epsilon, and then you have plus 2m v naught h ket ka square. You have psi a is equal to 0. Further, also you know that your wave function must be continuous at a, so you can write that your psi at a should be equal to psi at a minus epsilon and should be equal to psi at a plus epsilon. Okay, now if you differentiate at a plus epsilon, you can say that for all x greater than a, your wave function is given by c e to the power minus kx. So I'll write minus k c e to the power minus k, x की place में we will write this minus the derivative of wave function to the left of a. So to the left of a, you have wave function given by a e to the power kx minus a e to the power minus kx. So if you differentiate it, what you will get? You will get k a e to the power k a minus epsilon minus plus k a e to the power k a minus epsilon. And then you have this 2m v naught upon h ket ka square psi at a. Okay. Okay, so this is clear, and this entire thing equal to 0. And you know that at x epsilon tending to 0, this will become it. And overall, psi at a can also be written as, if I want to write c, like I can write in different forms that we'll see as we go along. So here you see there is a loss of symmetry, because if you wanted to write it in the terms of wave function, we cannot write, because to the left you had a negative here. To the left of a, the wave function had a negative. So there is a we'll have to see. Okay, and what we can do instead is we can simply change this particular c e to the power minus ka into this, because c e to the power minus ka is given by a e to the power ka minus a e to the power minus k. So I'll prefer to write that. What I would do is I will write minus a, and I'll write e to the power minus, sorry, e to the power ka minus e to the power minus ka. Then you have minus k a e to the power ka. You have minus ka e to the power. Oh, there's a mistake here. Minus ka, and then you have plus 2m v naught upon h ket square. And since everything is written so I'll write psi a, because psi a can be written as psi a minus epsilon also and psi a plus epsilon. If I write psi a plus epsilon, I will have to write c e to the power minus k a plus epsilon. But since I have changed it in this form, so I would change my psi a as psi a minus epsilon, and it will be equals to a e to the power of k a, forget about epsilon, minus a e to the power minus k. Okay, so overall, this long expression there. So now let us solve this particular expression. So what we'll get minus see minus ka e to the power ka. This is not negative here, ka, and here you have, I think this term will remain. These two terms will remain, and this term minus plus, and this is again minus. So this will become minus 2ka e to the power ka plus 2m v naught upon h ket square, and this there is an a here, e to the power ka is here, and e to the power minus ka is here. Okay, so overall this term will now a gets cancelled. E to the power ka, if you drop down, if divide it entirely, after certain simplification, I hope you will get this. Okay, Now, what does it mean? It means that what we were doing, we were trying to find the bound state for the potential given by this expression. And while we were solving the Schrodinger equation, we got a solution in the form of an equation whose solution we are still to find. Basically, what we were finding the number of bound states. We were interested in finding the number of bound states. And while we were finding the number of bound states for this particular potential, we solved a solved a Schrodinger equation. And if we solve, it says that the values of k, which are from which you can obtain the number of bound state, is given by this particular equation. Now you are again stuck with this particular equation. And you see, this is not an algebraic equation. This is not a polynomial equation. Okay, this is not an algebraic equation. So in mathematics, there are two equations. One are called as algebraic equation, which involves some some powers in x, and does not involve any other functions. Such equations are called as transcendental equations. So we'll have to see what to do. We can take numerical analysis. We can also take we can plot it on MATLAB somewhere, and we can find the number of solutions. But I will here use a simple strategy, and that would be to plot the graphs. So if at all you are not able to find where this k, what will be the solution to this k, so what we'll say, let's say this is your function fx, to the right your fk, and to the left you have a function gk. So wherever they both coincide, that will give you a solution. I will explain you with an example. Let's say I want to find where your cos x is equal to sin x in the range x belongs to 0 to pi by 2. You can simply simply an answer, that answer is x equal to pi by 2. But let's say if you never knew an answer, but I wanted to know that there is a root. So you know that there is a root. I know that sin pi by 4 is 1 by root 2, cos pi by 4 is 1 by root 2. But instead, if I follow a graphical approach, from 0 to pi by 2, your sine will come like this. And from 0 to pi by 2, my cos will come like this. So obviously there is a root. There is a single root. And we know from our trigonometry that that particular root is x equal to pi by 4. So overall, we know an answer to this particular problem by graph also. So what we'll do, we'll plot two graphs. We'll plot a graph of fk equals to k, which is a linear graph, and we'll plot the graph of gk equals to gk given by mv naught upon h square 1 minus e की power minus 2ka, and we'll find where my fk and gk coincide. At how many points my fk and gk coincide, and if my fk and gk coincide at 10 points, then there will be 10 number of bound states and so on and so forth. Let us see how things unfold. So we fairly know that my graph of fk equal to k would be a linear graph. So there is no problem. There is no problem here. So fk equals to k is simply this. I don't think there is a problem here. Let us make the graph of this gk. So gk graph I'm making here. So that would be okay. So now let us make the graph. So how does my gk behave? Gk is mv naught upon h square 1 minus 2ka. So now as k tends to infinity, e की power minus 2ka goes to 0. So overall, as k tends to infinity, my gk tries to asymptotically approach mv naught upon h square, because as k tends to infinity, this will become 0. So gk will approach this, and at k equal to 0, this is 0. E की power 0 is 1. So this is 1 minus 1 0. So overall gk is 0. So at k equal to 0, my gk is 0. At k tends to infinity, my gk is mv naught upon h square. And how does my gk rise? So basically what I would do is, I would simply differentiate it. So g dash k can be written as mv naught upon h square. Well, right? mv naught upon h square twice a e की power minus, I think, ka minus 2ka. Okay, this is positive, this is positive, this is positive. All of them are positive, so I can write my g dash k is positive. That implies gk is an increasing function. And if I try to differentiate it twice, g dash k, how g dash k would behave? Now again, since these are all constants, if again I differentiate it, I will get a minus 2a again. So overall, this will be a negative thing. So my gk or is an increasing function, or I can say my gk increases at a decreasing rate. At a decreasing rate. So my gk increases at a decreasing rate, starts from 0 and tries to approach mv naught upon hk square asymptotic. So I'm not saying it will merge, it will never merge anywhere. It will try to be as close as possible. So it will be asymptotes to this particular value, that is this particular value, that is mv naught upon hk square. I hope it is clear. Now there are two scenarios. You can see that your fk is equal to k. This is a graph that you already know. This is a graph that you already know. And gk is a graph which depends upon a. You can clearly see that it depends upon a. And you can see the slope also depends upon a. Okay, slope also depends upon it. Now, you just understand a point. There are two possibilities. Your gk can be made below fk equal to k, and gk can be made above fk equal to k. I don't know which way my gk would go. If my gk goes entirely beyond fk equal to k, there will be no solutions. Or you can say no, that there is a coincidence at k equal to 0. But understand that k equal to 0 corresponds to equal to 0, which certainly is not the case. Okay, so forget about this coincidence. But overall, if my gk lies below fk, then there are no solutions. If my gk is some way above fk, then okay, then it may be a possible thing that yes, there is a solution. Then there is a solution, and if there is a solution of k, it implies there is a bound state. So therefore, we'll achieve what should be the condition on a such that this bound state exists. Okay. So now, how to go about this? So I'll explain you in an easier fashion here. So let's say if I have this kind of, let's say easier case, I have this thing. Okay. Now you already know. Let's just take an example of sin x. So how would sin x behave? Sin x, whether it lies above or below. So answer to this particular thing can be understood in the manner. Let's say what is the slope of this particular function? This is fx equal to x. Now my question is whether sin x lies above fx equal to x or below. So for that, wherever you compare two functions, you just see the slopes also. So this is fx equal to x, the slope is 1. And this is constant 1, this is throughout. But the slope of sin x is cosine x, which is lying between -1 and 1. In principle, it is always less than 1. Only at this point, your sin x derivative will be equal to 1, because sin x ka derivative is what? Cos x. So at x equal to 0, it will be 1. Otherwise, sin x ka jo derivative hai, that is the derivative of the sin x, will be equal to cosine of x. And cosine of x is the cosine of x always lies between -1 and 1. That implies if I say my gx is sin x, I can say my g dash x will be always less than equal to 1. That implies is the slope of line is 1, and slope of sin x, which is given by cosine x, that slope will always be less than 1. So basically what happens is, if you want to make, what does slope means? Let's say if I'm making a like making a curve, what does the derivative signify? Derivative signifies the tangent drawn at a point. Let's say if I have to find the tangent at this point, it is equal to the derivative of the function at that particular point. Okay, so let's say I'm saying what will be the derivative of a function at this particular point. So what you can say, just draw a tangent, whatever might be the slope of that particular tangent, that is the derivative of the function at this point. Okay, so overall, if my slope is less than 1, so obviously the tangents drawn would be tangents drawn will have a value, will have the slope less than 1. So basically, if I'm saying my slope is, if I'm saying that my curve's slope is less than 1, that implies my line y equal to x will lie above. Again, like making you understand, because see, if you have, let's say this is your curve. At each point, if you draw the slope, it is, if you draw the tangent, and if the slope of all these tangent is less than 1, then obviously this line, which is fx equal to x, will lie above only, because the slope of this particular line is 1, and slope of all these lines is less than 1, so this graph will lie below. So you can say that when compared sin x and 1, your sin x will lie below fx equal to x. And that you can fairly see in your plot also. Only at x equal to 0, there will be a coincidence. Otherwise, overall, sin x derivative is cosine x and it is always less than 1. So it is less than 1. So the slope of at each point, that is tangent drawn at each point, will have the slope less than 1. So you can compare not sin x in this line. Instead, you can compare the slope of tangent drawn at any point on sin x and this particular line. So this particular line has a constant slope 1. So this so giving you I have explained you certain things above. Now tell me, what will be the condition of intersections? I have a, let's say if this is my fk equal to k, my fk equal to k is this, and my gk is given by mv naught upon h ket ka square 1 minus 2ka. If my slope of gk, that is g dash k, is less than 1, then obviously this particular function will lie below the function fk equal to k, and there will be no solutions from here. So this will give me no solution. So I will not find a bound state provided my g dash k is less than 1. But if my g dash k, and also understand my point. That we are doing all these things at, let's say this point is k equal to 0, right? So this point is k equal to 0. So if my g dash k at k equal to 0 is less than 1, what will happen? My curve will start, my curve slope initially also is less than 1. So basically, if I compare this particular graph, and this particular graph is a straight line whose slope is 1, and this particular graph slope is given by, I think if I'm not wrong, the slope was 2m v naught a h ket square e ki power minus 2k. This is how the slope was there. So if this slope is less than 1, what does it imply? It will always lie below this line. So if at k equal to 0, my g dash k is less than 1, then throughout my gk will lie below the graph fk equal to k. However, and I will not lead to any solution, so there will be no such bound state. So if there is no such value of k such that this satisfies this equation, if there is no solution to this this particular equation, that implies there is no solution to this particular equation, and we cannot find a bound state. But if you want to find a bound state, we must have a solution, at least one solution. How would solution be there? So there is a possibility that solution may exist, solution will exist, and what sure I'm saying definitely would exist. It is only when at k equal to 0, that is just at the start, if my g dash k is greater than 1. So if my g dash k is greater than 1, and let's say this is my mv naught upon, I think it was h ket ka square. Now, if my g dash k is greater than 1 at k equal to 0, certainly my graph will start just above the line. And overall, this graph will have to overall go and get asymptotic to this particular axis. So it will have one solution. It will have one solution anyway. So what is the possibility that I will have a solution? The only possibility that I have a solution is this, that g dash k must be greater than 1. And if I'm writing g dash k greater than 1, it implies 2m v naught a upon h ket all these things at k equal to 0. Because see, at k equal to 0, if g dash k is greater than 1, then I'm starting above the line. And since I have to converge anyhow, this particular graph will start getting asymptotic to mv naught upon h ket square. So it will converge at least for a single point. At least it will converge for a single point. So there is one solution here. There is one solution, provided your g dash k at k equal to 0 should be greater than 1. So if it is g dash k at k equal to 0, if it is greater than 1, then it implies 2mv naught a upon h ket square and e ki power minus 0 should be greater than 1. It implies 2mv naught upon h ket square a must be greater than 1. What does that imply? It implies that the possibility that there is a bound state and there is a single bound state, is that your A must be greater than, I think, hk square upon twice mv. So if the value of A is greater than hk square upon twice mv naught, only in that particular case you will have a bound state, otherwise not. So A was what? Where your Dirac delta potential was situated. So the magnitude of that particular A would decide whether your system is in bound state or not. So this ends up this lecture. I hope you must have learned a lot in this lecture. You just go and study the standard 12th book of on tangents and normals. If you are not able to understand, I will again make you understand. Please let me know if there are any doubts. Okay, and also understand there will be no bound state. So I'll write that also. What is the condition that there are no bound state? So for that, your g dash k at k equal to 0 must be less than 1, and which will yield you that A should be less than hk square upon twice mv. So overall, try to understand this problem, and we'll go ahead and let's see how things can change when we are changing the definition of the Dirac delta potential. For that, we'll meet in next lecture.